My name is Sushant Gupta. I come from Wood Mackenzie. I work as a director in the Singapore office, and I specialize in refining and chemicals. Now, as you all know, refining margins have tumbled quite significantly in the past 2 years, and this is the time, and this is confluencing with the time when petrochemical margins are also going down, and we are going through a down cycle, a perfect storm for the refining and chemicals industry. So the papers in the panel which we have today is designed to talk about how do we add value to your refining and chemical assets, how do you improve the profitability of the refining and chemical assets, and how do you improve the competitiveness. This is very important, particularly given that you have to earn the right to decarbonize going forward. Now, without further ado, I'll first introduce our first speaker, Mr. Abhijit Ram, who will be presenting on indigenously developed technology for processing of UCO. Now, UCO today commonly is known as used cooking oil, but I think he meant unconverted oil. Abhijit is a senior GM in process design development at Engineers India Limited and has more than 30 years of experience in designing, executing, commissioning mega refining and petrochemical complexes. He is responsible for licensing, presenting, and development of new technologies at EIL. So please welcome Abhijit on stage for a quick presentation. Thank you.
So here I am Abhijit Ram from Engineers India Limited, and very welcome, very good morning, warm welcome to Mr. Chairperson and my all colleague speakers and delegates here. So, what is this about? Now, we know there are a lot of things being talked about Atmanirbhar Bharat nowadays, everywhere, in every stage by government, and it is encouraged everywhere. So, we have also a Make in India zone in this, I think, hall 2, where many manufacturers and technology persons are there who have put up their stall to showcase their Make in India approach. So this presentation is nothing but a narrative of the one more success story of Make in India, which was launched by government way back. To start with that, I will say that I would just like to remind you one phrase which was narrated by Neil Armstrong while he landed on the moon. Of course, he took 6 months. It is said that he took 6 months to coin that statement, that one man live for a man and a giant live for a mankind. But surprisingly, I thought of this particular statement only in the morning today while restructuring my entire presentation in the mind. So this is a small step for EIL, but is a big step for Atmanirbhar Bharat as such for the government. So now, without much delay, I will start the presentation. So what is the presentation about? Let me first summarize it to start with. So there are 4 different sections which we will deal in this particular presentation. Number 1, what is the uniqueness of this technology? Number 2, what are the challenges we faced while producing the technology or developing this technology? Number 3, what are the innovations we did as a part of this unit? And last, what is the future of this technology in the refinery context as of today? So before we go to the actual technical presentation, I would just, this is known to many people here, but for the people who don't know, I just brief profile of EIL. It is a leading engineering consultant and a PC Navratna company. Then we have an international presence, 7,000 assignments and projects worth over 200 billion executed. We have already focused, we have been working mainly in oil and gas with refinery, petrochemical, gas processing, and those sectors, but we have now diversified to infrastructure, strategic crude oil storage, fertilizer, ports, LNG. So this is how we are at this point. Then before I go for the technology part and the innovation part, I will just tell you that many of us here sitting there may not be knowing that EIL is a proven technology licensor for delayed coker unit. And we have been licensing successfully this delayed coker in India. Many of our plants are there. The journey started with 1978. Of course, the units are capacities are small. Now, today we have I think we are on the execution of the largest capacity we have ever made, which is 0.78 MMTPA. Otherwise, we are starting with 1978. We had at Barauni, Big Boy, Guwahati, Barauni again, and now NRL revamp. So this is how we have traveled the path of coker licensing. Now, coming to what is the uniqueness of this technology? So before I take up this diagram, I will just go to the next slide. Yeah, I will come back to the slide next. This is how. So this technology has been indigenously developed with IOCL R&D. It's a joint technology by EIL and R&D. This combination of ebullited bed hydrocracking unit along with DCU is a highly optimum in terms of profit margins, product maximization. I will talk about that combination a little bit later, why this is important, this combination. It is a bottom from ebullited bed residue hydrocracking unit, which is a technology new to India. Now let me here put a stop for a while. This technology, this combination of ebullited bed hydrocracker UCO going to a delayed coker unit is the first time in India. We have not any operating plants on this particular technology, and probably it will be an ambitious statement. I would reserve my statement whether it is the first time in the world, but we have not found any references in all the technical literatures where it is 100% UCO is processed. It is a mix, but it is 100% UCO is processed in a coker unit, and that too when the coker is repurposed for this particular this facility. So this is where we have won that this is the first will be the first operating unit, and that will be based on indigenously developed technology. So then it is the bottom of the bed, which is the technology new to the high severity feed. Why it is so uniqueness? Now I am coming to the point why it is so unique is that it is high severity feed in terms of CCR, asphaltenes with no known reference of commercially operating DCU unit exclusive. What does it mean? It means that typically in India we have cokers which are operating on a CCR of 24 at max, not more than that at present. So this particular coker has been designed with a CCR of 30. 30 has not been designed so far. It was a challenge right from the beginning. People were not ready to believe that 30 CCR can be designed. If you look at the literature in the world, you will find only one reference of coker operating at 34 CCR. Now between 30 and 34, there is nothing. So second thing is that why asphaltenes? Of course, this is asphaltenes is 13 to 14 as compared to the normal asphaltenes we get from VRS 5 to 12. But this is a bit better because it is a hydrotreated asphaltenes. So the sedimentation part you can take care a better way than a raw asphaltenes. And then the last point is that what I am talking is high propensity for sedimentation. That we have taken care in our design, that I will come out. So if we summarize this, how does this comparison look like? This is the comparison. Why it is so unique? We have CCR 14 to 24 typically in coker feed. We have 30 here, asphalt is 5 to 12, 13.3. Then pour point, you can see the pour point. You will find why it is hitting. It is 85 as compared to 54. And then fouling factor. This fouling factor is double. So this double of fouling factor will reflect in the design of the equipments. That I will come later on. So now I am coming to the basic flow scheme, why it came up originally. So this is how the unit looks like at present. The complex look like at present where we are implementing this. Simple CDV we are going to DCU off gas taken to ATU, and then it is used for fuel gas and LPG. And the light distillate, middle distillate, heavy distillate, all of it was going to the existing hydrocracker unit. There was no other destination left for this distillates coming from the DCU. And the bottom was going to petcoke as usual. So this was later on, we modified the scheme like this, where the CDU VR was no more going to DCU, it was going to ebullited bed residue hydrocracker, which is under execution in the complex, and it has got a 70% conversion. Now here I would wait for a while because there are two types of people might question why 70%. So there are pros and cons taking a evaluated bed hydrocracker with a 70% conversion. We can go to 99%, 97% conversion also, where we won't be able to use this combination. But this combination was used because purposefully to use the existing DCU with a revamped perspective and with the evaluated bed, which is giving 70% conversion. So that UCO is going to DCU. From the DCU, we had at the same time some PFCC coming up at the same complex. So we could route the HGO to a video hydrotreating unit and back to the Petro FCC, and the middle distiller was only taken to hydrocracker unit. So this is the combination we did in that complex. So somehow I have covered now I will come to the why UCO processing in a coker is beneficial. I will just touch upon 3-4 points. Typically what happens, UCO either comes from hydrocracker or evaluated bed, and the quantity is small sometimes, so it is blended with the fuel oil for disposal in refinery. But here the case is different. We have taken the UCO to a DCU to give the value-added products like LPG, KRO, LJ. Of course, there is a small disadvantage when we use this UCO to a coker because the coke make is very high. The coke make goes up to 41-42% because of this. Not only because of UCO, it is also because of the 30 CCR. So future of so this will provide a future of that I will talk now when I come to the future section. Future of bottom of barrel processing for refineries. Then reduction in severity, of course, this gives flexibility while you are configuring the entire refinery and working out the capex, because this is 70% as it is 97%, the severity is less, conversion rate is less, capex is less. And we have already applied for patent. Patent is on a very advanced mode. In a few months, we are going to get the patent for this technology. Now coming to what are the innovative concepts we have used for implementing these technologies. And before that, I will go for the challenges. Okay, let me tell the innovations, then I will go to the challenges. The innovations are there. One is that we used exchangers with spare shells. Existing pre-heat was modified with spare shells because of this high fouling factor of 0.002. So we could gauge that in future while operating, you have to replace the exchangers or you have to take it offline for cleaning. So we have provided spare shells. Then we have introduced the internals in the fractionator. We have in the current fractionator, there is no washing bed. It is only the trays. So we have introduced a washing bed, which will give you a better control on the CCR. While you were taking out distilling the HCGO from the fractionator. And then we have introduced a sponge absorber, which was not there. It was a huge LPG loss from the unit. So we have introduced a sponge absorber in the unit. Next innovation, what we talk about is that in the heater part, this was very high challenge because for whoever has operated coker and knows about coker, he knows that the heater is the heart of the unit for a delayed coker unit, where it is not a normal heater, it is a reaction heater as compared to a CDBD heater or any fractionator heater like any hydroprocessing unit. So here, the problem came, what is the metallurgy we have to use? Because such a high fouling, we have asphalt tins for sedimentation purposes. So what is to do? And to have that mass flow velocities, flux flow velocities, we need high temperatures, TMTs. So we had to change the metallurgy for attaining the high TMTs. And then we made that heater a twin cell design. That is also the first design we will put in the coker and we will implement and execute it. So we have not done this earlier. So twin cell heater furnace design, where we can take care of the turn down of the coker without going for a second heater. Within the same heater, we go a twin cell, we put up this one twin cell and use the other twin cell and go for a 50% turn down. And in the coke drum, we have some patented designs in the coke drums that we have utilized here also. Like we have vertical plate design with Y forging of the coke drums, where a skirt to shell joint, we have a Y joint, that is also patented. And we have a very robust monitoring system which other licenses may not be using. We have a very robust monitoring system in the coke drums at the bottom from the skirt level to the, from the tan line to the conical portion to the skirt. We give a huge number of temperature transmitters with a algorithm how to monitor that so that we can take care of the different deformations which take care in the coke drums as we go on operating the unit. Now we come to the challenges. So I have Arun, fortunate to have in this panel along with me, who knows about these challenges and the difficult story we faced while doing the pilot study. So let me tell you how it was done. It's very interesting and exciting because the feed what we are going to get in the complex and the delayed cooker will operate is not available for pilot study. It's not available in India. And also in the world, one or two few sources are there. So we had to source it from South Korea. In the South Korea also there is one plant of Lamas operating, CLG operating, where we had to use a specific location which is not exactly matching with the point from where we should get the feed. So we had to take some location from the sample from South Korea, take it to US, the sample, synthesize there in the lab of the US, Lamas, to get the feed which will be fed to the unit while we operate the unit, then take it back to India, take it to IOCL R&D pilot plant, and then run the pilot study. That is how the entire journey, and the sourcing of feed was so difficult in the entire journey. And while we ran the pilot study, we had many difficulties, like it was getting choked. The pilot plant was getting choked with such a high CCR and aspartame, so multiple runs had to be done. There was a very furnace fouling tendency because it's a heater, overcome by maintaining furnace oil thermal profile, close monitoring of pressure profile and optimizing VFW engine. These are the things we managed how the pilot plant study we did. And then there were two different modes of design we used. One is that desk literature. We first designed the entire yields and everything based on the desk study, based on the literature available in the public domain and some particular special domains we used. And then we again did the pilot study to validate that yields data, what we got from the desk literature, and it was closely matching. So,
Abhijit, if you can just wrap up in a few minutes.
Yeah. So next I will go to the, I think I'm almost, so innovations and challenges have been done. And now, what is the future, I will say, is that we are also in the process of making this unit suitable for, this is basically fuel grade. The complex where we are putting the unit, they have a problem in disposal of fuel grade. So we are trying to make it anode grade in collaboration with one licensor. Of course, Arun is one of the part, will be part of that. We have not established that. We are hoping to get the anode grade from here because anode grade is not easy to get without a feed composition change with CLO. Here we will have modified the temperatures at the furnace and some other modifications we have done in the plant. Let us see how it goes while we can improve on that part while we operate the plant and commission the plant. So this is one of the ambitious target for this particular unit. And then, so these are basically the challenges which I have already said: thermal cracking in coker furnace, close monitoring required. Congealing issues are very pronounced in UCO, handling duty batch pour, high pour point. And multifold increase in coke yields, I have said it is 41% as again typically 30% of a coke yield. And then, there was many engineering challenges which I am not very much detailing here because one more major part of this particular revamp, repurposing of this coker for this particular technology was, it was an 85% revamp. Typically we go revamp for 50, 60, 30, 40 like this. It was an 85% capacity revamp which had got its own challenges. So these are the challenges which we have put like constraints in the existing plot area. These are all engineering challenges. The creation that is nothing to do with the technology, creating a footprint through extension of land, petrol limit, modification of internals of key equipment like fractionator. So this is how this indigenous technology was developed and is ready to be implemented in our one of the complexes which in the Northeast, which we are already operating. Thank you.
Thank you, Vijit. And in fact, one of the striking feature in the presentation was around the CCR of 30, right, which is extremely high, and I think it's definitely innovative to use the residue streams to convert into lighter products. Now, moving on to a separate theme around, refiners are thinking about value from integration, and we have Keith who will be presenting around eliminating the need for naphtha crackers. You might be surprised. But then naphtha, converting naphtha to ethane and propane directly for the production of petrochemicals. Now, Keith is an industry executive with over 35 years of experience in oils refining, petrochemical, gas processing, and renewables. His passion for India started on his first trip back in 1999, leading the commissioning team for FCC complex at Reliance Jamnagar. I hope you made more trips after that. And Keith now leads the Honeywell UOP's activities in the refinery of the future and crude to chemicals. Welcome, Keith.
Thank you, sir. This is actually my 41st trip to India, and very much appreciative of Dr. Maitra, Dr. Gard. Thank you very much. Very instrumental in my love affair with India and sharing the love with me. So with that, first off, I have to make the lawyers happy. I will be making lots of forward-looking statements, and just please treat them as such. When we look at sustainability, decarbonization, doing more with less, it changes the philosophy for how we think about technology, how we design technology, and how we meet the challenges of tomorrow. When we looked at all the things that go into, I want to be more efficient, I want to be more sustainable, we could distill that down to 6 fundamental efficiencies. The first one is carbon. We want to put the right feedstocks in the right process units to do the least amount of work on them. When we get that right, we look at hydrogen. We want to put it on to do good things, take it off to do good things, and do that as few times as possible. When we look at the C4 handling in a steam cracker, we have olefins, we saturate them, we put that paraffin back in the steam cracker, we take the hydrogen off again. It's a wasteful stream. There's better ways. When we get that right, we have to bring utilities down. When that happens, the emissions come down. Water, we have to treat water as a scarce resource. Very pertinent issue in India. And all of those 5 on the outer ring are in tension with capital. How are we going to pay for it? What's the economic return to our shareholders? And what's the budget? All right, when we look at a mixed feed cracker, most of the cracker projects that have been viewed going forward, especially with a lot of the market consultancies, are naphtha crackers or mixed feed crackers. Fundamentally because there's only one country in the world that exports ethane, net ethane. That's the United States. And we're in a situation where, for the first time in history, ethylene demand is outpacing ethane production on the market. So we've got to figure out other feedstocks that can not only go to produce ethylene, but do it more efficiently. All the different streams on the left can go into a steam cracker. Ethylene is what we want. That's what a steam cracker does well. Anything that's not ethylene is something we deal with. Propylene, we leverage it because it's valuable. We leverage it because it's made, and it's common to us in the petchem industry, but it's not most efficiently made in a steam cracker. Butadienes, we can make it, but you have to have the end market for it. One world-scale butadiene project effectively saturates the market for the next 5 to 6 years. Pie oil, fuel gas, we don't want them. The pie oil doesn't work well in a coking unit. It doesn't work well in a hydrocracker. It goes to fuel. And the fuel gas production has a 20% higher carbon footprint than buying natural gas. What's even worse about that fuel gas is every carbon you lose to fuel gas takes 4 hydrogens with it. So that fuel gas is a hydrogen thief, and in India, hydrogen is very expensive. All right, so what should go into a steam cracker? In this case, I've plotted both the hydrogen efficiency in black, the carbon efficiency in red. Steam crackers love ethane. The worst 2 feedstocks you can put into a steam cracker, propane and C4s. Why? Look at all the gas make. And the heavier feedstocks, the heavier the feedstock I go, the more feedstock I have to process to get me that same ton of ethylene. When I process more feedstock per ton of ethylene, what happens to the size of the unit? It gets bigger. And what happens to the cost of the unit? It gets a lot bigger. So we want the orange and the green. We don't want any of the dark colors. When we look at a steam cracker, that combined oil temperature, 850, 845, 835, 825, it's very hot. We're not just baking cookies, we're burning them. Every feedstock that you put in a cracker has a very high carbon footprint because I have to heat it up so much, and I also have to use a lot of steam. The heavier I get, the more steam I have to use. Steam is fuel gas. Steam is water. Steam is CO2 footprint. When we plot the amount of ethylene that's produced, even going to just naphtha, I now have to process twice as much naphtha to get the same production of ethylene. Twice as much naphtha, but also at a higher steam rate. All right, so the steam requirements go up exponentially with heavier feedstocks.
Good morning, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 5 p.m. All visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the halls. Please take care of your belongings. Thank you.
Every now and then I get this voice in my head, I don't know. The pie gas, the pie oil. So pie gas, short for pyrolysis gasoline. Is it good? Well, it makes aromatics. It makes gasoline blend stock, but it also does that at 7 times the energy footprint of a reforming unit. All right, so we have to be careful. We know what we can do with it. The question is what we should do with it. Pie gas is not your friend. From an energy standpoint, cost standpoint, and a CO2 standpoint, it's very bad. All right, fuel gas production. A lot of people don't understand the evil of making methane in a steam cracker because I need it for fuel to run the furnaces? And my answer I just gave. All of the methane you produce has been through the cracker. It consumed steam, it consumed energy, and it consumed volume. When I look at buying natural gas, 20% lower carbon intensity than trying to burn the methane that you produced off the cracker. All right, so we don't want to produce methane on the cracker. When we look at that pie gas, almost 2 times the cost of production of making the same aromatics in a reforming unit. All right, so again, getting back, put the right molecules in the right process unit to make the optimized feedstock. So, this slide shows the fundamental basis of what most people embody as a modern crude to chemicals complex. When you look at the 9 projects in Saudi, the 2 in Turkey, one in Egypt. This was fundamentally the basis through which they started. And all the ones in China. And many of the ones in India. And the problem that we get here is all of this stuff downstream of the steam cracker. As we've gotten larger in scale, 2.2 million tons per annum of ethylene is a world scale cracker now. So what we find out is an integrated complex like this, 400,000 barrels a day, is running upwards of 27 billion US dollars. And much of that cost is in all of these C4 handlings, the aromatics, the hydrotreaters that have to go to deal with all the products that you produced that wasn't typically your objective from a steam cracker. Again, steam crackers want to make ethylene. So, what do? We're in the first point of human history where there's actually a demand in the market for on-purpose ethane production. Using feedstocks that you have indigenous. In the case of India, you actually make more light naphtha. You export light naphtha to the tune of being able to make about 8 million metric tons per annum of ethylene. So in this case, we've taken 7 process units out of the design of a crude to olefins complex or a crude to aromatics complex. We've eliminated the liquid cracker, which cuts the cost on the back end of the cracker down tremendously. We put a NEAP or a naphtha to ethane and propane unit in front, make the ethane with an option to produce propane as well. NEAP does not make the olefin. We tried for decades to do direct conversion of naphtha, catalytic naphtha cracking, to the olefin. We couldn't beat the low-cost performance of a PDH unit for propylene, and we still haven't beaten the lower cost of making ethylene from a steam cracker. But we can make ethane, and we can do it from a feedstock that's discounted about $12 to $15 a barrel from crude, and that's the light naphtha. We also use 45% less crude to do this. Much more efficient per ton of ethylene. That's the race that has to be fought as we look at converting other feedstocks, non-traditional feedstocks, to olefins. The advanced hydrocracker, fundamentally designed for C7 minus conversion. Why? Because that NEAP unit's going to process C7s, 6, 5s, 4s, and even 3s. If you don't want the propane and the propylene, we simply take the propane back as feedstock. It converts about 99.5% per pass. So there's no high combined feed ratio buildup. It's effectively a once-through process. C3s to C7s, and we're looking at extending into heavier hydrocarbons to feed the process. Fundamentally, it's going to become a foot race between the NEAP unit conversion and the hydrocracker conversion. So still working on what's the heaviest naphtha we can process, but right now today we're going up to C7s. Highly variable. We can move from mostly ethane and a little propane all the way to a lot of propane and almost no ethane. That matches against the markets that you want to be in. Do you want to be in the propylene business, or do you want to be in the ethylene business? The other cool thing about NEP is it doesn't care about the iso to normal ratios. When you look at a normal crude to chemicals complex, the max conversion of feedstock is dictated by the hydroprocessing units, the slurry hydrocracker, the primary hydrocrackers. The problem of over-converting is that steam crackers don't like isos. If you process isoparaffins in a steam cracker, the performance declines. In this case, you're normally limited to about 72% conversion on the hydrocrackers for economic optimum or optimum economics. In this case, we can run full conversion and still get extremely high yields because the NEEP doesn't care about the ISOs and the normals. We're seeing a resurgence of butene requirements. That's China. China's lifted the moratorium on MTBE. They're now focused on MTBE. So in the last year, we've licensed 4 BDH units to be able to feed the MTBE markets for India. Every time I get a heavier olefin desired, the cost of the unit comes down, the operating severity comes down. PDH. Putting propane into a steam cracker is on the left. Putting propane into a PDH unit is on the right. Much more efficient. If I try to put propane into a steam cracker, again, here's all that methane that I make. When I look at the product values, a marked increase. When I eliminate the mixed feed cracker and all of the capital that goes into the recovery section, I can pay for the entire PDH unit. It's not an economic barrier. It actually reduces the capital of the installed asset. So we're really happy with this combination. 90% more hydrogen recovery, 40% more light olefins, 75% less pi gas and pi oil. Every piece of equipment that's got a red line through it is something that gets eliminated when we move from a liquid cracker or a naphtha cracker into an ethane cracker. That's the cost savings. And all the working capital inventory that comes with all those vessels that get eliminated. When we look at an actual application, we often get told we have to process a certain quantity of feedstock. How much petrochemicals can you move? Standard 2.2 million crude to chemicals in that original base case I showed you takes about 200,000 barrels a day to make 2.2 million metric tons per annum of ethylene products. Here, we're doing it with 88,000 barrels a day.
Keith, sorry, if you can wrap up in a minute.
Yeah, I'm claiming a minute back from the voice in the air.
Yeah, sure, you get an extra minute.
All right. The propylene or the propane, that 1,000, I could drop that 88 down to about 65,000 barrels a day. 65,000 barrels a day gets me 2.2 million metric tons of ethylene. The economics, almost 4% at the project level, higher than the original base case. Most of those projects that I talked about in Saudi are stalled or canceled because the cost is too high. We have to get to bankable. When we see naphtha crackers, we go through ITBs, we go through basic engineering designs, and they get canceled because they never get to FID. The bankers and the financiers aren't willing to lend that quantity of cash. So we have to be smarter, adopt new technologies to be able to be better tomorrow than we were yesterday. The splits on the yields I've included so you can look at that on your own time. And the first of these units is going to go into Petro Rabigh in Saudi Arabia. Petro Rabigh has a problem where they're not getting sufficient ethane supplied from the Saudi government. So in this case, they're having to process light naphtha, C3s, C4s. So we're working with Aramco and the folks at Petro Rabigh to put in the first one. I never thought Saudi would be the first adopter of a new technology. That bankability issue, if they don't do something different, they don't get to a finance bankable project. So with that, we have to put the right feedstocks in the right process unit. Those 6 efficiencies drive the progression of change. We have to focus on the carbon footprint, and continued innovation has to continue to be adopted, or you're going to continue to repeat the non-bankable projects of the past. So with that, I thank you very much.
To evaluate options for ethane-based cracker, using this technology. Now, in the line of petrochemical integration, we have our next speaker, Mr. Alok Tripathi, who is going to talk about innovative ways to benzene maximization at BPCL Kochi Refinery. Alok has been with BPCL for more than 19 years. He is a chemical engineer with a considerable experience in operations, projects, execution, and commissioning. He has handled various multi-crore projects at BPCL refineries, and currently he is working as a section head at the CDU block. Welcome, Alok.
Expanded significantly in its petrochemical footprint, but still benzene yield optimization remains a challenge. With increasing demand of benzene from various industries, refining our approach to benzene production is not only an opportunity, but a necessity. So today I will take you through a simple, innovative strategy which we have implemented at BPCL Kochi Refinery, which has enhanced our benzene production. So this was the trend before we have put this strategy. So benzene production was 2.5 to 4% of the CCR feed. That means it was in the range around 2,500 to 3,300 metric ton per month. So this is the schematic flow diagram how we are producing benzene at Kochi Refinery. So C6, C11 feed cut goes to our CCR unit. In the CCR reactor, reformate is formed. That reformate is fed to our reformate splitter. The bottom cut, which is a heavy reformate, is a lean in benzene, but it has good RON. So this stream goes to basically to our MS pool. The side cut, which is a light reformate, is rich in aromatics, that is benzene and toluene. So this stream we are sending to our aromatic recovery unit. So in aromatic recovery unit, with the help of solvent extraction, we use sulfolane, and coupled with the distillation, we produce benzene and toluene. So coming on to our CCR reactor, where this benzene is produced, basically there are two main reactions which are responsible for benzene production. The first one is dehydrogenation of cyclohexane, which results in the formation of benzene. Another one is this methyl cyclohexane, which results in the formation of toluene. So this is the simplest reaction, and the conversion is 100%. Another reaction which results in the benzene formation is dehydrocyclization of normal hexane. So the rate of this reaction is very slow. That is only 1% conversion happens. So the general methodology which is available with the refineries to increase benzene productions are, one is increasing naphthenes in our feed, but then it becomes crude dependent factor. So that has a limitation. Another way of increasing benzene is you increase the CCR reactor severity. So as we have already seen in the previous slide, naphthene conversion is 100% and paraffin conversion is limited. So increasing reactor severity will increase our benzene to a certain limit, but that has a limitation. So in totality, if we see, conversion to aromatics is limited and is basically dependent on the feed. So what we did at BPCL Kochi Refinery, we took trials for benzene maximization. Our aim was to find a benzene precursor in our CCR feed. So first what we did was we tried to reduce CCR feed IVP. From 90 we brought down to 80. But what happened when this we made the feed light, there was increase in C5, C6 component. C5 component is basically very less isomerization happens, but it resulted in some negative effects. There was cracking, my hydrogen yield got reduced. Although there was increase in light reformate, which goes to my aromatic unit, but it didn't result in the increase in aromatics. And my reformate yield, that also got reduced. So another thing what we did was, we tried to identify a stream which is high in benzene precursors. So such stream, we got one stream, was our DIH bottom from the Penex unit. So basically, in Kochi refinery, we commissioned UOP Penex unit, that is basically assimilation unit, in 2021. Penex DIH column bottom is normally routed to MS blend. This stream we analyzed. What we found, the components which were present in this stream were basically N-hexane, cyclohexane, 2MP, 3MP, and some C6, C7 hydrocarbons. The RON of this stream was around 70 to 72 tons. RON was 70 to 72. And the quantity which we were getting was around 6 to 12 tons per hour. So when we went into the detail, we did component analysis, we found that C6 component was more than 80%. And out of this, cyclohexane was around 25 to 45%. So this cyclohexane is the precursor for our benzene production. So this stream, in order to recover cyclohexane from this DIH bottom stream, we prepared a new scheme. We routed this DIH bottom from DIH column to our upstream of naphtha stripper. And it was a hot stream, 120 degrees. And then this stream, once it goes to reactor, this gets converted into aromatics. And then again, that reformate splitter, light reformate increased, and then it was sent to ARU. So post implementing this scheme, this our benzene production, it increased from 5 to 6% with percent of CCR feed. And this scheme we implemented online without taking any shutdown and with a minimum cost. Coming on the benefit analysis, once we implemented this scheme, my benzene production increased to around 2,000 metric ton per month. So annually, if you see, it was around 24,000 metric ton. So net profit what we got annually was around 50 crores. So we can see that by implementing simple strategies, refineries can increase benzene production and maximize their benefits. Thank you. Thank you for patient listening.
Thank you, Alok. I think first of all, you get a free delegate pass for next year for helping us catching up on time. So our next speaker in line is Dr. Amit Mishra. He's a chemistry doctorate from National Physical Laboratory, NPL, New Delhi, currently holding a position of Chief Quality Control Manager at Indian Oil's Mathura refinery. He would like to discuss about the impact of fuel acidity on the electrical conductivity of aviation fuels derived from high TAN crudes after dosing of static dissipator additives. Thank you so much, Mr. Mishra, for having us.
Thank you, sir. A very good morning to all of you. This is the presentation. As the topic states, electrical conductivity response in high TAN crude derived ATF towards SDS. So I have come with my colleagues also who are also associated with this work. Dr. Navneet Maheshwari and Dr. Bhaskar Pramanik, they are also along with me. The agenda of this presentation will be a general overview, This was a study, small study carried out at laboratory scale. Depending on the classification of type, availability of high tank crudes, how the study goes. Then aviation fuel specifications, where conductivity requirements is there. Dosing of static dissipator additives SDA, aviation fuel acidity experimental setup and methodology what we carried out under this study. Then TAN's influence on the conductivity and the factors which are affecting the conductivity. This presentation explores the impact of fuel acidity, as already written, of ATF derived from high tank crudes. Aviation fuels, they are derived from different type of crudes we choose for processing depending on the property of final aviation product. We know that crude oils are extracted from different locations of earth and can have distinct properties. So it is a general classification based on either API, based on sulfur content and based on the TAN count. If we classify the crude oils based on acid number, then it can be classified in 3 groups. Low TAN group, less than 0.5 mgQH per gram TAN value. Acidic crude, having TAN value, total acidic number more than 0.5 mgQH per gram, and high TAN crudes more than 1. Basically, as already shown in this picture, the acidity of the crude oil is originated due to presence of various type of naphthenic acids having different carbon numbers, and presence of these acidic components make these high tank crude less attractive for the processing. These are normally less preferred because high tank crudes have a lot of challenge during refining because of the high TAN value, high acidic value. They have the very few lighter components available, high density, high viscous. They have high asphaltene contents, high salt content, high metals. So these properties are basically responsible for some adverse effects during refining operations, like during desalting, corrosion, foaming, catalyst poisoning, fouling, and poor conductivity also. So due to such adverse effect, refiners always avoid processing high tank crude and subsequent production of ATF from high tank crudes. But because of the geopolitical regions and low cost of high tank crude, refiners are compelled to process high tank crudes either with doing some metallurgy upgradation or taking all other necessary steps to mitigate the disadvantages of acidic crudes. Jet fuels in refineries are normally conventionally produced by sweetening process from either Merox unit, hydroprocessing through hydroprocessed. All the aviation fuels must meet some specifications, and there are several international specific standards available for aviation fuels, namely Jet A, Jet A1, Jet B, etc. And Indian standard is IS 1571 for Jet A1. Basically, 2 critical parameters are there which are to be looked. High tank crudes are acidic from the table we can observe the acidity requirement is maximum 0.015. It is specified for Jet A1 in Indian as per IS specification, and electrical conductivity requirement is 50 to 600 picosiemens per meter. So let us discuss little bit about the conductivity of aviation fuel and acidity of aviation fuel. Conductivity of aviation fuel has a paramount importance with respect to the safety because of the fire hazard during fuel storage, transportation and handling. During refining operations, sulfur and trace metals contained in aviation fuel get reduced to make the fuel low conductive. Therefore, aviation fuels have very low electrical conductivity, and conductivity becomes after processing less than 5 picosiemens. But from the safety point of view, aviation fuels are required to be conductive. To impart conductivity in low conductivity aviation fuels, dosing of static dissipated additives, that is called SDA, these are required, and as per the specification maximum 3 ppm is allowed at refinery end and up to 5 ppm at marketing end, and it will result into the maintaining the electrical conductivity in the desired range of 50 to 600 picosiemens per meter. If we discuss about the acidity of aviation fuel, like crude oil, acidity of aviation fuel is also originated by the presence of naphthenic acids and some crassilic acids also, that is methyl phenols, etc. These acids get carried over in ATF either because of the acid treatment during the refining process or due to naturally occurring organic acids coming from the crude oil. Acidity is a measure of combined organic and inorganic acidity, and it is expressed in the milligram of KOH required to neutralize the total acidity. Acidity is the indication of corrosiveness, and our study is going to discuss about the effect of acidity on fuels electrical conductivity on SDA dosed aviation fuels. So what we did in our study, we collected fuel from 3 different sources, one from Mirox, one from DSDS, mild hydroprocessed, and severely hydroprocessed hydrocracker unit. All these samples were collected before SDA addition, and then we added SDA 450 to impart the electrical conductivity, and fuel's conductivity was measured as per standard ASTM D 2624, and acidity was measured through titration as per ASTM D 3242. The initial study was to assess the SDA effectiveness towards ATF derived from different sources. ATF collected from different units, and during different crudes run was collected, and SDA was dosed from 1 to 3 ppm. From the table as well as from the graph, it is evident that the initial conductivity of the ATF was 0 to 2 picosiemen per m. After dosing, it got increased 450 to 480. In case of DIDS, we received the highest response toward the SDA dosing, while it was slightly lower in other fuel sources. Out of the three process which I already discussed, physico-chemical properties of Merox treated ATF are highly dependent on the nature of crude oil processed, while the mildly hydroprocessed DSDS ATF and severe hydroprocessed that is hydrocracker unit ATF. Therefore, the physico-chemical properties are independent of nature of crude. Although all samples have similar acidity, initially slightly lower electrical response in high tenor crude was observed. As per the last slide, what we did, we carried out an experiment. We collected the samples from to understand the effect of 10 value on electrical conductivity. Merox feed was collected along with the Merox ATF during high tenor run crude, and different blends were prepared using the Merox feed with Merox rundown. Then SDA was dosed and conductivity loss was observed. Initially, all these samples have, all the blends have the conductivity of 0 to 2 PS per meter. Then we dosed 1 ppm of SDA, and it is observed the sample having the lowest acidity, that is 0.008 mgqh per gram, showed the highest conductivity, that is 490. The response was found lower, and only 395 was observed in the higher conductivity high tenor value. These same blends were subjected to also with respect to the time, and as per the plot it can be observed that the conductivity of the blend samples gradually decreased with the progress of the time. The decay rate was directly influenced by the 10 values of the blends, that is, decay rate is quite slower and similar for the base ATF for blend number 1. In case of blends with higher 10 values, they exhibited a faster decrease in the conductivity with respect to the time. It was also observed that drop in conductivity was quite fast in initial 4 to 6 hours, and then it drops consistently over the period of time. Other factors which can influence SDA response towards electrical conductivity were also studied, like sunlight effect. So sunlight is known to adversely affect the conductivity of fuels treated with the conductivity improver additives. The same is also observed in our study, it is a known fact. So ATF fuel having low acidity, that is blend number 6, was subjected to sunlight exposure in a colorless bottle. The sample in amber color bottle is termed as non-exposed ones. So there is clear difference between the sample which are exposed in amber bottle as well as in the clear bottle to know the effect of sunlight on the electrical conductivity. Coming to the other factors, temperature. SDA response is known to be the temperature dependent also, because it is proportional to the sample temperature, and as per the plot it is observed that the 10 values of 0.0022 to 0.035 mgqh per gram, it can be observed that electrical conductivity response towards temperature is almost identical for low acidity and high acidity fuels. So this will help uh, to identify the optimized dosing during pipeline transfer, because during extreme temperature, other factors which was found affecting the electrical conductivity was viscosity, and same pattern was observed. So our observation in sunlight exposure to fuels treated with conductivity improver drastically reduces electrical conductivity of the fuel. This factor does not have the much consequence on the fuel which are
Mr.
not
Amit,
exposed to sunlight.
if you can just conclude in a minute.
Coming to the conclusions and takeaway, refining process must carefully manage the 10 value of aviation fuel while processing heightened crudes. Pre-treatment of acid removals like inclusion of ECP extra to remove the acidity. As per the specification, 0.015 mgqh per gram is the requirement of the acidity, but it is better to keep as low as possible to maintain the effectiveness of SDA during transportation. Conductivity decay is faster with increase of the acidity of aviation fuel. That means SDA dosing is dependent on the 10 value of the acidic value of the ATF. As the conductivity is highly affected due to presence of co-additive and contaminants, refinery to ensure effective clay filtration for effective removal of contamination, maybe frequency of clay filter changeover is required to be increased, and it is also is advisable to have the separate tank storage for heightened for the aviation fuels which are derived from the heightened crudes. Thank you, sir.
Profitability, so quite an important step. So in the next in line, we have Mr. Arun Arora, who brings over 30 years of experience in technology and engineering to his role as Chief Technology Officer at Chevron Lummus. He'll be talking about increasing profitability of the refineries, at the same time reducing capex, energy, and space. Welcome, Mr. Arun.
I believe it's the last presentation, and it's a Valentine's Day. So, hope you guys remember in the evening. But let's come back to more interesting subject about what we do. So will not get too much into technical, but I think touching on your presentation, we're happy to be contributing towards Atmanirbhar of Bharat with the IO on that. And also, Keith, you mentioned about the challenges about reducing capex and the solutions. This is important because in today's, so let me get quickly to a little bit of overview, then a very detailed technical. So quick introduction, and then I'll go over some technological solutions which we have and how to integrate refinery and petrochemicals, which is energy efficiency as well as then circular economy, and then key takeaways. I don't know how many of you know Chevron Lummus Global is also a joint venture for 25 years, but now we have also have a agreement or JCLA with INI. INI is an Italian company, and they have a technology in their slurry technology, so residue upgrading. So we have signed that agreement with them almost 4 years back, and we are working on multiple technologies with them, but I'll go over that. And Chevron brings operating experience. We are the only refiner or only licensor who has a refiner as a partner. So operational as well as engineering and technology background. So our philosophy of licensing has been that first we test our technology, our catalyst in refining in Chevron system, and then we go global and license to our customers. And that's to de-risk the technology. So a quick overview of our technology platforms here, or the bottom one, the residue hydrocracking or the residue upgrading. If you see that, we are unmatched in the industry. Any solution to either hydrotreat, RDS or VRDS, to go to RFCC, or a conversion process, any conversion process to, which I'll go over briefly. There are multiple solutions available. LC Fining, which is operating or under construction in India in NRL, and then LC Max, which is under construction at HPCL Vizag, which is going to start up this year, hopefully. And then few other solutions which I'll describe. ESTs from INI. LC Hobby is another innovative solution in collaboration with Aramco. And then we have various coke. We have almost 10 cokers in India, and now anode coke, which you mentioned, as well as needle coke. Needle and synthetic carbon, which is actually were in early 90s, were also 3 plants in Japan commissioned for making needle coke, but now they're coming back because of electrification of the cars, and we need those anodes, as well as steel electric arc furnaces. And then we have some solutions to integrate all this, which we call TC2C, thermal crude to chemical. That one is to maximize petrochemicals and ethylene by minimizing crude intake, as well as save energy and capex in plot space. And then there's a called IST, which is integrated slurry technology, similar to TC2C, but with the slurry. And any of these products which we make with the crude, upgrading of the bottom, needs further treating. So we have iso-treating, iso-cracking, and iso-dewaxing for lube. We're also doing renewable feed co-processing. We have done it in India, we have done it in Europe and US. So all of those have been co-processed, and even 100% processing has also been done. In the renewable side, we have 3 technologies. Isoterra is where the HEFA process is. We can process any kind of bio feedstock to make SAF and renewable diesel. And plastic pyrolysis, and even the tire pyrolysis oil, all that is, Lummus is our partner and our parent, and that we have a plant of plastic, waste plastic processing, making bio, and we have taken that into our Chevron lab and processed all the way to make final products back to the steam cracker. Now, a various configuration which I just mentioned, a little overview of that, is LC Fining. I don't know how many of you are aware of, or EV technology. There are almost 20 units operating in the world. And we have taken that concept, LC Fining, and added an SDA in between to remove the asphaltenes, which are usually causing the sedimentation and falling issue in the unit. So it increased the reliability and also reduce hydrogen intake, because your asphaltenes are the one which are least hydrogen. They're 3, 4, 5% hydrogen, and if you want to pump it all the way to make VGO 11%, you have to pump a lot of hydrogen. So that is the concept in LC Max, and that is under construction at HPCL Vizag. And we have also integrated hydro treating as part of that LC Max. So further reducing the capex as you integrate. The integration comes because LC Fining or LC Max has already hydrogen loop, high pressure hydrogen loop. You can just add another reactor to hydrotreat and make final products. So you don't need a whole new compressor, all the way separators, exchangers are all minimized. Even the heat, you don't have to cool it down the product, fractionate, store it, pump it back. All that is within the loop hydrotreated. And then many of the LC Fining or ablated bed units, whether it's H-oil or LC Fining, you can do, depending on crude, 70 to 75 to 80% conversion. But then the rest of the 20%, what do you do with that? So then we combine our RDS technology and put it at the bottom of LC Fining, and then we can make IMO compliant 0.58% sulfur VLSFO. And that's also under construction in Korea. Now, coming back to all these are 75 to 80%. LC Max can do 93% conversion with SDA. And in the slurry, we can do all the way to 95 to 97% conversion. And that I'll go over. We have two solutions for slurry. One is LC slurry. And then we took one from INI called EST. EST stands for INI Slurry Technology. So what does INI Slurry Technology looks like? Very simply, we can take fresh feed, which is VR. You can also take pie oil from steam cracker, mixed feed steam cracker, and some even circular plastic pie oil can also be processed if needed. And then the beauty of slurry reactor compared to, let's say, our ablated bed reactor, slurry reactor has no pump. There's no EV pump. The way they're doing the ablation is using hydrogen as a gas. So the hydrogen circulation rate is high, but there's no pump. Minimum internals, very few internals just for hydrogen distribution. So the catalyst is also unique here. It's a nano catalyst, liquid catalyst. And another beauty of this is that it's available. You don't have to buy through a licensor. It's available in the market. There are two kinds of catalyst. One is which is available in the market. One is which we have developed, which is isoslurry catalyst. But what's available in the market is operating at 4 units in China. This EST is operating in 4 units in China, and 2 are about to start up, and 2 are under design. So in China, there are a lot of love for this slurry technology. So no EB pump, and then you pay, and its process is very simple. That's the reason we have collaborating with INI, is because LC slurry we were not able to commercialize because of various, Chevron wanted to invest themselves to make a plant, then we can go and license, like I said earlier, but then Chevron could not invest, and INI, in fact, went ahead and invested in their own plant in Sannazzaro in Italy, and they demonstrated that the unit can process and run reliably at 95 to 97% conversion. So that's how they licensed to China, and then the China duplicating for 5 units. So it's hard to beat a commercial reference. So these are the 2 units I'm showing here which are operating. This was started in Maoming, Sinopec in 2021, and then ZPC, which has, they started with train 1, they copied it to train 2, now they copied train 3. So they have 3 trains of 60,000 barrels each, 3 million metric ton, huge. When we joined hands with INI on slurry technology, and we wanted to bring our ISO slurry technology where the best features are and make it further robust as well as improve efficiency. So what INI does is there's a recycle so that we can bring back the catalyst back. Catalyst being a nano catalyst, it doesn't loses its activity. So because of that, we recycle back, but then you have to still take a bleed. So if you are doing 95, 94, the units are operating in the range of 93 to 95% conversion. So you still have to take 5 to 7% bleed. In this case, I pressed the wrong. So in this case, what we have added is, we have added a special filter which we call now enhanced EST, enhanced slurry technology. So in this filter, we concentrate the catalyst and reduce the recycle, and that way the bleed is only 1% because now very concentrated bleed. So this is almost 99% conversion. So that technology is now hopefully will be implemented in China soon. So this is another refinery of the future which we've been promoting. Most of you may have heard about it, TC2C, and where we start from backwards. Usually refinery has been, we take the 400,000 barrels crude and crude tower and vacuum tower, and you go along the way and make different. Here we are focusing only on the products you want to make, and we come backwards and then adjust the configuration. So whether you want to make a certain amount of ethylene, certain amount of, let's say, diesel also can be made here. This can be adjusted. Even any other product like aromatics, if you want to make, which can be made here, as well as diesel product after hydroprocessing. So, we have eliminated CDU, VDU as well, which are very high energy intensive units, and refinery is a 100-year-old technology. We have been doing this for many, many years, and we have to challenge few concepts, how we invest in a configuration which is going to last for next 50 years or so. So these are new concepts, how we separate crude itself, and it is done into only 2-3 cuts instead of various multiple cuts, no vacuum column, no crude column, and we use a medium which can be further utilized downstream processing unit. So that's a unique concept and a very simple concept. If you're interested, we can show, not in a public forum, but we are talking to various clients already. One unit which is under construction in South Korea will start up end of 2026, early 27. So this unit is already under construction. Lastly, I think petrochemical integration, like in an ethylene cracker, if you make pie oil, which has no home, which goes to fuel oil, or let's say if you have FCC slurry oil, it has no home. LC fining or EST loves that because of high aromaticity of that feed. So we can take that pyrolysis oil or slurry oil back to LC fining, convert that, and even plastic recycle is being done, like I mentioned earlier. In our Texas, there's a unit operating, Lamas New Hope Plastic Pyrolysis. We can do treating and hydroconversion and back to petrochemical. So,
Arun, if you can just wrap up in a minute.
Yes. Okay. So this is the last slide anyway. Crude and product flexibility is very, very important these days. So you have to select a technology that is versatile and can process different feedstock, and conversion. There's no home for fuel oil or high sulfur fuel oil. Today the market is good, but not for next 10, 20, 50 years. And lowest capex, opex is very important. And the reason it is lowest capex at the highest conversion is, like I talked about earlier, how we are integrating the different units within the same high pressure loop. So number of equipments, let's say if I compare TC2C with a conventional refinery, it's a 30 to 40% lower equipment count. So you can imagine utilities around 25 to 30% lower. So CapEx and OpEx, as well as since you reduce the equipment, your plot space requirement goes down. And for, imagine you don't have to do the whole engineering and all that savings in that. So the integration has taken to a next level here. All valuable products you make now, especially if you have EST or ablated bed technology, because we can take all these low value streams. Actually, the unit which is in Korea, that's what they're doing. Most of the streams there are slurry oil and pie oil. And SDA, even SDA pitch, low lift SDA pitch. And then plastic pie oil upgrading. Any kind of pie oil we can upgrade either in EB or in EST, whether it's a tire pyrolysis oil or whether it's a plastic pyrolysis oil. So with that, thank you very much.
Thank you, Arun. I think with this we have concluded the presentation. So I'll just wrap up by saying that as you have seen in all the presentation, there was a very simple mantra. You maximize your revenue and minimize your feedstock cost, right? Which is very simple, but easier said than done. There have been a lot of efforts in these presentations to show that how do you maximize the value of low value products today, and maximize the market which you're targeting, the products, produce the product which the market wants. At the same time, allowing you to process high TAN crude, for example, giving more flexibility to your feedstock, all aligned with the future of the refining. And I would like to say, given the times are very challenging for refining and petrochemical, these all efforts will help us, help the industry to create profitability and also earn the right to decarbonize in the future. With this, I would like to thank all my presenters today and let's have a big round of applause for them.